Here's the multiple choice quiz on reaction mechanisms and energy profiles. There's a couple things in this unit or this section of the unit that kind of come in twos, two rules of this and that. Here are the two rules of an acceptable mechanism. It must simplify to the desired balanced equation, and the rate law based on the molecularity of the slow rate determining step must match the experimental rate law observed in the laboratory. So we can write rate laws based on the stoichiometry or the molecularity, the molecules colliding on the reactant side of the balanced equation. We just don't know if it's right until we confirm with lab data. In the second question, they refer to the fact that not all collisions result in a chemical reaction. We say that collisions need to be effective. Particles need to collide with sufficient energy and in the proper orientation. But if the two colliding molecules have less than the minimum amount of energy required for the reaction to occur, that could be a reason why there was no chemical reaction. And same with the last choice, that the molecules did not collide in the proper orientation. Then they may collide, but if not in the proper orientation, we may not have a chemical reaction. Here's kind of a mechanism that's given to us as a little particle model, and they want to know which species acts like a catalyst. A catalyst is something that I have to add, and then I get it back. So it's not going to appear in the final balanced equation if I simplify this. So I kind of wrote it out as like the symbols. I mean, the little bubbles are fine. The little particle models are fine too. But I wanted to just kind of simplify and write it like the real particles. So I'm looking for something that I add and then I get it back. It's something that I add and it cancels, so that again, it's not part of the final balanced equation. In this case, it should be the chlorine atom. That one open white circle, that would be a chlorine atom. I add it and then I get it back. The other option would be an intermediate. Intermediates also cancel out, so they don't appear in the final balanced equation, but an intermediate will first show up as a product. It's formed and then consumed, whereas a catalyst will first show up as a reactant. I add it and then I get it back. Kind of like this example. Here, the oxygen atom is an intermediate. It's produced in the first step and consumed in the second, so it would not appear in the final balanced equation. Here we've got a balanced equation and we have a rate law. Which of the following could be the first elementary step of a two-step mechanism if the first step is slow? Okay, so if the first step is the rate determining step, then its rate law needs to match the experimental rate law. So if this given rate law is my true experimental rate law, then that should match the rate law based on the molecularity of the slow step, which here they're telling us is step 1. So I'm looking for one molecule of NO2 and one molecule of fluorine. And again, we can write these rate laws based on, we call it molecularity, the molecules colliding on the reactant side. But we have to confirm with lab data. So the laboratory data always wins. That is the true rate law. All right, here's another mechanism. They give me the elementary steps of a proposed mechanism. Which of the following is the rate law for the overall reaction that is consistent with the proposed mechanism? So if this mechanism is correct, what rate law should I experience in the lab? And so I just look at the molecularity of the slowest step. Your overall reaction rate cannot be any faster than that of the slowest step in the mechanism. So I would expect this to be second order with respect to the NO2. And because the CO, carbon monoxide, is not appearing in that experimental rate law, maybe we would assume that it's just zero order with respect to the carbon monoxide. As long as sufficient carbon monoxide is present, changing the amount doesn't affect the rate. So this is what I would expect if that rate law is proper, if it is acceptable. I would expect to go in the lab and find second order with respect to the NO2, zero order with respect to the carbon monoxide. Here's a part of a rate law. I have a two-step mechanism, say part of a mechanism. Missing the first step. Which of the following correctly identifies both the chemical equation for step 1 and the rate law for the overall reaction? Okay, well, I can kind of work backwards to figure out what the equation would have been. Step 1 and step 2 need to simplify to the overall balanced equation. So if step 1 had the 2NO2 forming the NO and the NO3, then that would simplify to the desired overall balanced equation. So that's a little bit of trial and error. You can look at the 4 proposals for step 1, and if I plug them in there and compare them with step 2, cancel anything that's the same on both sides, cancel out my intermediates and my catalysts, which would simplify to the desired balanced equation. Then finally, if this is an acceptable mechanism, I would expect to find a rate law based on the molecularity of the first step. That's the slow step. I would expect it to be second order with respect to the nitrogen monoxide or nitrogen dioxide. And again, similar to the last equation, I would expect it to be zero order with respect to the carbon monoxide. So kind of a similar question, similar equation, but just given a little different way. I kind of like this one, like going backwards to figure out the reaction, and then what would be the rate law I would expect if this is an acceptable mechanism. That's a cute question. I like that one. Maybe I should have saved it for the test, huh? Hopefully I got enough good ones for you. Here's 2 mechanisms. I've been given a balanced equation, and I've been given the experimental rate law. In the end, we kind of want to know which mechanisms are acceptable. And so I checked to see that they simplified to the desired balanced equation, and they both do. And then I also wrote a rate law based on the molecularity of the slow step. And in each, it was the same as the experimental rate law. So here's another one where the Y2 does not appear in the experimental rate law. So I would assume then that it is zero order with respect to the Y2. As long as sufficient Y2 is present, changing the amount doesn't affect the rate. So in this case, both are acceptable mechanisms. And that's the best we would do, is just to say that they're both acceptable. Now, in the end, we would maybe prefer a simpler mechanism. It's just less collisions that all have to happen effectively in order to get from the reactants to the products. Same thing with elementary steps. Each little elementary step we try to keep pretty simple, because kinetics is all about collisions, and the more particles that I have to get colliding effectively, the less likely it is that that's an acceptable elementary step. If I had an elementary step that had like 3 or more different reactants, I would say that's probably not likely to be all in one step. Maybe that's broken apart into multiple little steps, because again, we don't want to have to rely on 3, 4, 5 or more particles all having to collide in the proper orientation with sufficient energy. Just realistically, that becomes difficult the more different reactant molecules you add to the mix. Again, we've got a reaction and we have an experimental rate law. Which of the following mechanisms is consistent with this rate law? Meaning, like in another word, which one would be an acceptable mechanism? So I want them to simplify to the desired balanced equation, which I could always double check that. So if I look at my first reaction, I could cancel out this oxygen as an intermediate. And then, yep, I've got the 2NO, I've got the oxygen and the 2 NO2s. I can look at my second one, and I've got this NO3 intermediate, but now that simplifies to the desired balanced equation. Cancel out my intermediates. It's almost kind of fun, isn't it? The third one gives me the proper balanced equation. Cancel intermediates. And let's see here. Ooh, I've got 3 total nitrogen monoxide on my reactant side. I don't have any O2. And then I've got the 2 products. But the reactant side is not going to simplify to the desired balanced equation. So I can at least say that this third one is out. Or I should say the fourth one is out. All right, so now I'm going to look at the molecularity of the slowest step to see which one would simplify to the experimental rate law. So I'm looking for 2NO, 2 nitrogen monoxide. So I'm not going to have that in the slowest step of the first mechanism. I do in the third mechanism, but I don't have any oxygen in the slow step. Sad face. So maybe right there we're thinking that it's got to be the second one. But remember, when you've got these reversible reactions that have a double-sided arrow, you know, the slow step in the second mechanism is the second step, which is involving an intermediate. And we can't have intermediates that would realistically show up in an experimental rate law. That's not something that I can control. And it's, in fact, really hard to study the concentration of an intermediate over time. So you'll never have an intermediate show up in your experimental rate law. It should really just be based on the molecules colliding on the reactant side and not any kind of an intermediate that's going to be formed and then consumed. But when your first step is an equilibrium reversible reaction, it really means that all of those particles are present at the same time. Nothing is ever going to completion. Nothing is ever zero. All 3 of these particles are present. So you can take what's opposite that intermediate and sub it in place of the NO3. And now I would get 2 NO and 1 oxygen. So you can only do that when your first step is a fast equilibrium. It's got to be a reversible reaction, because then all of that is really equivalent. The reactants and the products are all present. So instead of the intermediate, sub in what's opposite the intermediate. And it works. Here's another one that's kind of similar, where we've got a fast equilibrium. What is the rate law expression for this reaction if the second step is rate determining, which it is listed as slow? And so kind of similar, that I've got this intermediate, the 2 iodine atoms, formed and consumed, but they should not appear in my experimental rate law. I can't study them in the lab. But because that first step is reversible, you can just substitute in what's opposite the intermediate. So I can plug in the I2. And then I should get an experimental rate law that is first order with respect to the hydrogen and first order with respect to the iodine. Now, it doesn't have to match the balanced equation. I mean, sometimes it does, but we have to confirm these with lab data. That's how we would confirm this rate law. Go in the lab and try it. All right. Now, on to some of these energy profiles. An increase in which of the following will not produce an increase in the reaction rate? Well, it should be that activation energy. If I increase the activation energy, that would slow the rate. That means I need to add more energy to get the reaction started. But temperature, increasing the concentration, increasing the surface area, anything that increases the number of collisions will increase the reaction rate. Increasing the temperature, yep, that'll increase the number of collisions. Particles are moving faster, they're colliding more often, and if they're colliding more often, then hopefully there's a greater fraction of those collisions that are effective. Increasing the concentration, yeah, that should increase collisions. There's just more of the active particle present. Same thing with increasing the surface area. There's just more room now for particles to congregate and collide. Which then was kind of the answer to the second question. Increasing the concentration of reactant molecules will increase the reaction rate because you've got more collisions. All three of those will increase the number of collisions. All right, so here's my little energy profile graphs. This is for the reaction of O3 and oxygen atoms in the upper atmosphere. All right, so the question says, which of the following mechanisms for the catalyzed reaction is consistent with the equation and diagram above? All right, so we can use an NO, nitrogen monoxide catalyst, to help this reaction along. And so they've got the presence of the NO as the graph that I guess is a solid line. Or I should say absence of the NO. That's the solid line. So that would be the absence of the catalyst. The presence of the NO is the dashed line, which then means that I do have a catalyst. So number one, I'm looking for a two-step mechanism for the catalyzed reaction because it's got two humps to it. If your energy profile graph has two humps on it, that's just showing you that it was a two-step mechanism and that you've got the activation energy for each step in the mechanism. So first I'm looking for a two-step mechanism. Second, if you look at the amount of activation energy needed for each step in the mechanism, whichever step requires more activation energy was the rate determining step. That would have been the slower step, the one that required more energy to get started. So for the first step, it would have been from my reactants all the way up to the peak. That's the first activated complex or transitional state. Well, then in the trough here, like kind of down in this area, that would have been the products from the first step in the mechanism. Any intermediates would be formed in there. And then if I go from those products up to my second transitional state, that would give me the activation energy for the second step in the mechanism. So for sure the slow step needs to be the first step. So I need a two-step mechanism. I need the first step to be slow, and I want it then to simplify to the proper desired balanced equation. And it's showing that the NO would have been a catalyst. The NO is a catalyst in that it was added and then I got it back. The NO2 is an intermediate, formed and then consumed. What a great question that is. Oh, that is just chock full of good chemistry. Here's another little graph, and we've looked at these guys before. We've looked at these back in like the gas section where we're looking at a random sample of gas particles and that the energy of the gas changes as the temperature changes. This is kind of the same type of graph, that we've got two graphs here at different temperatures. If you take the peak of the graph, that's where you find the majority of the particles. If you follow it down, that'll give you the energy level. So the average energy level at temperature 1 is less than the average energy level at temperature temperature 2. Based on the graph, it says, which of the following statements
Antonio Harris, please
best
report to the
explains
button.
why the rates of disappearance
Antonio
of
Harris, please
NO2
report to the button
are
at this
different
time.
at temperature 2 and temperature 1. So why do rates change as you change the temperature? Well, one is that there's a greater number of collisions. The particles are just colliding more frequently. If they're colliding more frequently, then we should have a greater fraction of collisions that are effective. The other has to do with activation energy. So sometimes you run these reactions and it's obvious that you need activation energy. It's obvious that I needed a spark. It's obvious that I had to put the beaker on the hot plate. But then there's other times where you just dump your reactants together and poof, I just formed a precipitate and the reaction just seemed to go. I didn't need to add energy. But it might just mean that some of the particles already had enough energy to start the reaction. We don't always see that on our thermometer because our thermometer just reads the average temperature. But we know that, the energy of each particle kind of follows these graphs where most particles will be at your average temperature, but there's always a small section of particles that are above and a small section of particles that are below the average temperature. And so here, if they marked in activation energy, I can see that for each temperature, there are some particles that are at or above activation energy. But at that higher temperature, there's more molecules that possess energies at or above the minimum energy required for a collision to lead to a reaction. Or in other words, there's more particles that are at or above activation energy. When I increase the temperature, it's like that graph scooches over to the right and it kind of it kind of lengthens a little bit. The area underneath each graph is the same in that it would represent the same number of particles, but at a higher temperature, they end up representing a little bit wider range of average energies. The more particles at or above activation energy. Here's another one of these little energy profiles. Adding a catalyst should reduce activation energy. So activation energy in the forward direction would be represented by this one. So that's activation energy in the forward. That would reduce if I use a catalyst. But then so would activation energy in the reverse, which is represented by this second line here. To reverse it, I have to go all the way from my products, Z, zoop, way back up to my activated complex. So if that's at a little bit lower energy because I used a catalyst, then activation energy in the reverse would also be a little bit lower. Now 3, that's like the overall delta H. That's the overall energy change for this reaction. It's the difference between the energy level of the products and the reactants. That does not change whether or not you use a catalyst. That's always consistent. It's the same products, same energy change. It's just that we get there a little faster if we use the catalyst. But the energy level of the reactants and the products will always be the same. It does not include that activation energy pump on the top, because activation energy is energy that you initially have to add, but you do get that back. And then some if it's exothermic like this reaction would be. And finally, another question about a catalyst. The rate of the reaction increases significantly in the presence of a solid palladium catalyst. Which of the following best explains this observation? If there's any question about a catalyst and you're like, I have no idea, you're looking for something about lower activation energy. And that is the bread and butter of a catalyst. It lowers the activation energy so that the reaction can start fast.